Here I have a slide which shows how molecular shape can affect London dispersion forces. Now, interestingly enough, we have these compounds which are isomers of each other. We each have 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. So we have the same formula, the same molar mass. But if you guys see here, the melting point of octane is much higher than the melting point of isooctane. Now, and what happens here is, if you can imagine this, that the octane particles, this one has a lot more area, surface area to the molecule, whereas this one is kind of clustered up. So what happens is that the effect of LDF is felt more on the octane than the isooctane because the particles can actually get much closer to each other than over here. So when you have all these particles bunched up, consider this, the particles, the electrons and protons can't get close to another like atom. Whereas in this one, if you can imagine, if you had another isooctane, I'm not going to draw on the hydrogens, but the surface area is a lot more, so the particles can align a lot more and get a lot closer to each other. Let's talk about a couple more things. Let's compare when you have more than one IMF coming into effect. Here we have ethanol, which is C2H5OH, and methanol, which is CH3OH. So both of these have hydrogen bonding present. So both of them have H bonding. You have that hydrogen right there, OH, meaning it has hydrogen bonding. But also LDF, because they're both molecular. So we have these interesting things that you can see here. And let's look at the vapor pressure of ethanol at 20 degrees Celsius. Compare that to methanol at 20 degrees Celsius. You see ethanol has a higher vapor pressure than ethanol. Oops. So the lower vapor pressure of ethanol is because ethanol has stronger IMF than methanol. Now think about why we might have here. We both have one hydrogen bond possible. We both have this OH minus, which is responsible for the hydrogen bond. The red ones are oxygen, the white ones are hydrogen. But take a look here. Ethanol has this whole much bigger group than methanol right here. So you have your one carbon group attached to the oxygen, whereas here you have your 2 carbon group. That's why LDF, when you have like substances like ethanol and methanol, both have this OH minus, both have hydrogen bonding, you have to kind of compare it to the rest of it. Now, the molar mass of methanol is smaller than ethanol, so the effect of LDF is less in methanol than it is in ethanol. Here, in ethanol, you have more protons and more electrons attracting each other, whereas in methanol, you have less because it's smaller. You have this molar mass of ethanol, which is methanol, which is 32.04. Molar mass of ethanol, 46.07. So you have more LDF effect than here. They both have London dispersion forces and hydrogen bonding, but we see that affected more in the ethanol. Moving on, also, interestingly enough, how the atoms are arranged. These are two isomers of C2H5OH or C2H6O. So they're both the same formula, notice. But ethanol has a different structure than dimethyl ether. So this is something we'll go into a little more when we talk about bonding. But take a look at this. We'll notice the vapor pressure. Really high vapor pressure. Tons of vapor pressure here. Big vapor pressure at 20 degrees Celsius, over 100. Whereas the vapor pressure of ethanol is about 6. Now the reason why is this is just, if you notice that the oxygen attached to the hydrogen here, but here your oxygen is attached to 2 carbons. So here you have your oxygen attached to your hydrogen, so you actually have hydrogen bonding here in ethyl alcohol, whereas no hydrogen bonding, but we do have a dipole-dipole, IMF here. So interestingly enough, your dipole-dipole IMF is a weaker force than hydrogen bonding. Hydrogen bonding is actually a particularly strong type of dipole-dipole. So you can see this, that even though they have the same molar mass because they have the same formula, the vapor pressures are very different. So you have much weaker IMF than here, stronger. All right, moving forward, a couple of other interesting slides that I have. Hydrogen bonding in water. Hydrogen, water has this really strong hydrogen bond because it can hydrogen bond twice. You have one molecule of water here, and you have another molecule of water here. So think about this as a 3D structure. So there are 2 hydrogen bonds for each of this. So when the particles slow down, they tend to align themselves in this hexagonal structure, which actually occupies more space than just the water. They have all this open space here in that lattice structure, and that causes the density of water to be much less as a liquid. Well, not much less, but less than a liquid because the liquid particles are more compact. Interestingly enough, if you put pressure on solid water, that causes it to melt, and that's why we can ice skate, because there's so much pressure under that ice skate that it causes the hydrogen bonds to not form in their most stable way. And that's why when we get our phase diagram, the water actually, where we have our solid, liquid, and gas, we have a negative slope at this point. It goes back because if you increase the pressure, it'll actually turn into a liquid even at the same temperature. So as you go up, increase in pressure, it can melt. So that's interesting. Moving forward. So molecules such as like DNA and proteins, they actually can align themselves based on hydrogen bonding. You know how your guanine and cytosine and your adenine and thymine, they actually hydrogen bond, and that's what keeps the DNA particles together. So hydrogen bonding can be pretty strong, and you can actually have within a same molecule, like in proteins, you can actually have hydrogen bonding form within that molecule, and that's what some of the helix structures form from, in proteins especially. Take a look at this slide. Dispersion forces become stronger effects when molar masses increased and elongation of molecules. That is interesting. You know, if you have a really large hydrocarbon like a paraffin wax, it ends up being a solid compared to methane, which is a very small one. Both have LDF, but the more and more particles you have, the stronger the effect of that London dispersion forces. London dispersion forces is in all molecular substances. Dipole-dipole and dipole-induced dipole forces are found in polar molecules, which is why they have stronger IMF. And you have this particularly strong dipole-dipole called hydrogen bonding. Moving forward, another thing I did want to show you guys is when you have a molecular substance like graphite, you have this graphite. We have this planar graphite structure. If you can imagine, this is on one plane. So these are planes of graphite. And this is why we have this is why pencils use graphite, because you have your strong network covalent structure holding the sheets of graphite together. And that's also why graphite sometimes uses a lubricant for different substances, for different machines. If you guys ever do some machine work, sometimes they'll use it. What happens is those are very strong bonds, but the sheets are connected by London dispersion forces. They hold them together. So interestingly enough, those sheets are very strong together, but they have that weak London dispersion forces keeping the sheets together, and that's why you're able to write with a pencil and it sticks there. So that's it, really. I think there's one more slide here. Comparing it to carbon diamonds, these are both network covalent substances, but in the diamond, as you see, this is a small part. Each carbon is connected to 4 other carbons, so that's why diamonds are the hardest material on Earth, because you have those carbons are all bonded to each other. So that's a hard bond to break. That's it for this one, guys. IMF explains a lot about the world, so get used to it.